Hi, in Crash Course Physics episode 11 we go back to rotational motion and look at a few things that are maybe a bit more different than in the situation of planets orbiting around the Sun, but that are more related to wheels rolling on a surface. So first of all, why do we use this unit of radians instead of the good old degrees? Mostly mathematicians and physicists say that it's a more natural unit. We go from a scale that goes from 0 to 360 to a scale going from 0 to twice pi. And it just simplifies lots of formulas that have to do with rotational motion. So for example, the arc length over an angle theta, if theta is in degrees, that would be the formula for the arc length. If theta is in radians, it's a lot more simpler. Same goes for velocity. We've seen this, v equals omega times r, and also for acceleration. It's just omega squared times r. So this prefactor of pi over 180 that would otherwise be everywhere just disappears. It is included in the unit that we've chosen for degrees. The relationships between the units that have been presented, frequency, angular velocity, and period, are maybe at first sight a bit confusing and it's hard to tell them apart. It's easy to remember them if you think about what ratios they represent. For example, angular velocity is radians per time, while frequency is the number of turns per unit of time, usually seconds. And since radians are measured as 2 pi radians equal 1 turn, the frequency is just omega divided by this factor of twice pi. The period is the time that it takes for 1 turn to complete. So it's time over turn, so just the inverse of the frequency. Now I want to take a look at this seemingly paradoxical result that there's always a single point on the wheel that is not moving at all. This can be looked at in two different frames of reference. If we look at the frame of reference of the wheel that is moving along with the wheel and imagining that the road is moving below the wheel while the wheel remains stationary, we see that each point on the wheel is actually moving at the same velocity, just tangential in different directions. Now if we switch to the frame of reference relative to the road, each of these tangential vectors gets added a horizontal velocity component. The highest point of the wheel becomes twice as large in the same direction, while the lowest point gets added its exact opposite. So it has zero velocity. So this is the velocity diagram as seen from outside of the wheel. We actually see that the lowest point seems to be not moving at all. But this only is for a single moment in time. If we follow the motion of an isolated point on the wheel, we get this kind of shape. So this point is fastest on the top of the wheel, and as it reaches the lowest point of the wheel, as it rolls on the surface, the velocity actually becomes zero and reverses. But this only happens for a single amount of time, a single instant. And at each instant that the wheel is rolling, a different point has this kind of property. The shape of this curve is called a cycloid, and it actually appears in different other parts of physics and has some very nice properties that are absolutely unrelated to rolling wheels on a surface. So that was all for Crash Course Physics this week, and don't forget to subscribe and follow me on Twitter. See you next time.